Greetings everyone, my name is Farrell Liam and my student number is 210-553-1089. Today I'm going to be presenting about metal forming processes, Chapter J to Chapter L. My main reference for this topic is from the Handbook of Manufacturing Processes, How Products, Components and Materials Are Made by James G. Brala. Today I'm going to present about 3 chapters. The first one is high energy rate forming methods, the second one is straightening, and the last one is other forming processes. We're gonna go into the first one, high energy rate forming methods. Explosive forming. Explosive forming used an explosive charge to provide the energy necessary to effect the forming operation. Normally, the explosion takes place in water, and the water pressure then forces the work metal against the die walls. But rubber, sand, glass beads, oil, molten salts, and air can also be used as a pressure transfer medium. And this is the illustration of the explosive forming. As what I said, this is the explosive charge. And when the explosive charge explodes, it will force the work metal or the work sheet metal to stick against the die walls, just like this. The workpiece is formed into shape of die. I have one video of explosive forming and I'm gonna show to you guys.
Explosive forming is a metalworking process that uses energy from an explosive to form a metal into the shape of a mold.
This is the
The
simulation of
sheet
the
is placed
explosive
on top
forming.
of the mold and the air beneath the sheet is evacuated. This is done to prevent the air from stopping the metal sheet from being pressed into the mold once the explosive is triggered. Next, the tank is filled with water to maximize the effect of the shock and pressure wave. Finally, an explosive is placed above the metal. When the explosive is triggered, it creates a shock and pressure wave. When the pressure wave hits the metal sheet, it then forces it into the shape of the mold.
Okay, that's how explosive forming works.
Explosive
Now let's get into the next one, combustible gas forming. With high energy rate forming process or HERF process, hydrogen, methane, or natural gas mixed with air, oxygen, or ozone, when ignited, provide the pressure wave that forms the sheet metal workpiece. The speed of the pressure is less than using high explosives, and the duration is shorter, but still measured in milliseconds. The pressure wave occurs in the ignited gas rather than in water or some other medium. The process is more suited for in-plant operation and for larger production quantities than high explosive forming. More complex shapes can be produced. Large parts of sheet metal are feasible. And this is the illustration of the combustible gas forming. This is the workpiece blank, this is the die cavity, and this is the igniter electrical connection, where it will ignite the oxygen and the combustible gas in it. Electromagnetic forming, or EMF. Electromagnetic forming, also known as magnetic pulse forming. It is an impulse or high velocity forming method using pulsed magnetic field by application of Lorentz forces to the workpiece, preferably made of highly electrically conductive material without having working medium and mechanical contact. This is the illustration of electromagnetic forming. This is before discharge and this is after discharge. Before discharge, the sheet metal is still straight. After the discharge, the coil explode or the sheet metal got forced by the magnetic pulse and it stick against the walls. This is the video of electromagnetic forming. Okay, that's how the electromagnetic forming process works. The next one is spark discharge forming or electrospark forming. Spark discharge forming use electrical energy stored in a bank of capacitors to create a shock wave, which is transferred through a liquid medium. The energy released is in the form of a spark across two electrodes. Switching circuits instantaneously discharge that energy to the two electrodes. The energy sends a shock wave that forces the workpiece against the wall. Electrohydraulic forming, very similar to the spark discharge forming, except that the energy is released from an exploding bridge wire connecting two electrodes. Water transfers the force that forms the workpiece, and the operation cannot be repeated, but it provides somewhat greater forming force and the process is effective. This is the illustration of the electrohydraulic forming machine. This is the charger, where it charges the electricity, and this is the capacitor bank. If the switch goes on, the electrodes explode and it transfers from the water to the worksheet. After explode, the worksheet stick into the die walls. Now this is the video of electrohydraulic forming process. And that is the result of the process. Okay, let's get into the next one. It's pneumatic mechanical forming. This method can be considered a variation of drop hammer forging. Compressed gas stored in a pressure tank or the energy released in the form of gas from combustion of a fuel oxidizer mixture is used to drive the press ram to a high velocity. This is the pneumatic mechanical forming illustration. And this is the ram, this is the die, and this is the workpiece. This is the example video of pneumatic mechanical forming. The pin forming. Pin forming is a forming process that does not require any dies and can be performed at room temperature. Sheet metal is impinged on one surface with a stream of metal shot. Each shot piece acts as a very small hammer stroke, compressing the surface vertically but elongating it horizontally. This is the workpiece and this is the shot, the metal shot. The high metal shot is shot into the workpiece plank until the workpiece plank is formed like this. That is why this pin forming process does not require any dies. Let's go into the next chapter. Next chapter is straightening. Manual straightening covers a variety of operations performed with surface plates, levers, vices, anvils, hammers, twisting tools, grooved blocks, and heating torches. The workpiece is clamped at one end or where there is no deformation, and the deformed portion is moved in the opposite direction of the distortion. The workpiece is overbent so that it springs back to a straight orientation. Press straightening. Press straightening uses an arbor or hydraulic press to make the corrective bends. The deformed workpiece is placed on support blocks. This is the support blocks, so that the convex area is on the upward side. The ram descends and bends the workpiece in the opposite direction far enough so that the elastic limit of the material is exceeded. The blue one is the workpiece before straighten and the orange one is after straighten. The blue one is still bent and the press head. Press giving pressure in the middle until the workpiece is straight like the orange one. I'm gonna show you the example of the video. So this is the machine of the straightening press.
250-ton straightening press. Remote wireless controls. Variable speed. You can use this control anywhere around the machine. It's handheld. We also have a pressure regulator on this machine, so you can adjust the pressure. You can use this machine to straighten tubing, solid shafts, beams at 250 tons.
The press
There's
head
a lot of
giving
material you can straighten.
pressure into the workpiece metal.
Very sensitive controls. This straightening press is made in North America. We thank you people for watching this short video.
Okay, that's all. The next one is parallel roll straightening. Parallel roll straightening used for sheet, rod, or wire workpiece. A series of parallel rollers subjects the workpiece to progressively decreasing reverse bends as it passes through the rollers. As the metal is bent, it is stressed slightly beyond the yield point, exceeding from the rollers with a reasonably flat or straight shape. This is the illustration. This is the parallel roller, and it subjects the workpiece from the bent workpiece into the straight workpiece like this. This is the video. Next, the rotary straightening. Rotary straightening is a method for straightening round rods and bars. It uses two or more rollers with axes at an angle to each other and at an angle to the axis of the part. One of the rollers has a concave shape and the other cylindrical. Both rollers are driven and they rotate the workpiece and cause it to move axially. For more information, I'm gonna show you the example of the rotary straightening process. This is the rollers. And that is the workpiece metal. This is the two rollers. One has a concave and one has a cylindrical shape. Okay, let's get into the next one. Epicyclic straightening. Epicyclic straightening is a proprietary process for straightening axles, tubular drive shafts, and propeller shafts. The workpiece is supported at its ends and is rotated. A powered arm attached to the workpiece so that it is stressed in all directions beyond its elastic limit. The powered arm reduces the magnitude of deflection gradually. Stretch straightening. The workpiece is gripped mechanically and stretched in a straight line beyond the yield point. Twist deformation can also be corrected if the workpiece is reverse twisted when it is stretched. The process is normally limited to workpieces of constant cross-section. It also results in some material loss since the ends damaged by gripping must be removed. To the last chapter, other forming processes. We're gonna talk about powder metallurgy processes. Powder metallurgy is a manufacturing process that produces precision and highly accurate parts by pressing powdered metals and alloys into a rigid die under extreme pressure. This is the whole powder metallurgy process, from the base powder lubricants and alloying elements to mixing, compacting, and to sintering. After the sintering, it goes to the secondary operations, either then machining, second compacting, impregnating, joining, and other else. After the secondary options, it becomes a finished product. I'm gonna explain about metal powder manufacture. Metal powder manufacture is properties of products produced using powder metallurgy are dependent on the characteristics and properties of the powder. One of the processes used to produce powder for powder metallurgy is melt atomization. Atomization is the most common method for producing powder. Other processes include chemical reduction, electrolytic deposition, grinding, and thermal decomposition. All metals and alloys can be converted into a powder in every process. The next step is the powder blending and mixing. In this blending and mixing process, powders are combined with other powders, binders, and lubricants to ensure the final part has the necessary characteristics. Blending and mixing can be completed wet or dry depending on the type of powder metallurgy process and the requirements of the part. There are 4 common techniques of blending and mixing the powders. There's rotating drum, rotating double cone, screw mixer on the interior of drum, and blade mixer on the interior of a drum. This is an example of the mixing technique. I'm gonna show you guys the video of the blending and mixing powder from the powder metallurgy process. Okay, so that's how the powder and blending mixing. The next step is pressing compacting. In this pressing compacting process involves pressing and compressing the powder mixture into desired shape or die. Compacting reduces the potential voids and significantly increases the density of the product. The compressed and pressure form is referred to as a grain compact, an indication that the part was formed by compacting. And this is the powder. This is the first stage, die fill stage. This is the second stage, compaction, and this is the part ejection, where the grain compact is made and is ejected from the pressing machine. Both of these videos is a pressing compacting process. The powder goes in and is pressed and compacted. And this is the result of the pressing process. Okay, that's the process of pressing and compacting. The next step is sintering process. In order to produce a permanent bond between the metal particles, the grain compact is sintered or heated at high temperatures. Sintering process is a heat treatment wherein large numbers of parts in compacted form are subjected to temperatures that are sufficient to cause the loose particles to unite and bond, forming a solid base. There are 3 phases of sintering process. The first one is burn off, which removes air and volatilizes binders and lubricants as the temperature of the compacted part gradually increases. The volatilized materials must be removed from the furnace atmosphere before the second phase begins. The second phase is a high temperature stage during which the diffusion bonding takes place. This can require a period of minutes or several hours. For iron-based parts, the temperature ranges from 1850 to 2100 Fahrenheit. Copper, bronze, and brass parts allow somewhat lower temperatures. The last phase is the cooling phase, which lowers the temperature of the sintered workpiece while maintaining the controlled atmosphere. This is the illustration of the particles. This is before sintering, and this is after sintering. This is the sintering process example of a video. This is the machine where the workpiece. Just like this. Next step is repressing. The sintering process results in parts with some shrinkage from the green state as binders and lubricants are removed from the parts. To improve the dimensional accuracy of the parts, to improve surface finish, to sharpen certain details, to reduce the porosity of the parts, may be subjected to an additional pressing operation. Repressing can take place in the same die that was used for compacting. Secondary operations. Powder metallurgy parts can be machined, thread rolled, heat treated, and surface finished after fabrication. Machining takes place when undercuts, side holes, screw threads, and other features not visible with the powder metallurgy process are needed. Secondary operations themselves can help seal pores, prevent corrosion, and control component size. So the secondary option is for the finishing. The powder metal forging. In this powder metal forging process, the sintered powder metallurgy part becomes a blank for forging. The operations involves more drastic deformation than conventional repressing, and the powder metallurgy part is heated to forging temperature beforehand. This process has the advantage that the forging blank can be made to optimum size and shape, eliminating or greatly reducing wasted material and permitting the production of more complex forged shapes with reduced necessity for machining after forging. This is the powder metal forging process. Electroforming. Electroforming is a process that utilizes electroplating techniques to make a formed sheet component. In electroplating, the deposited material is very thin and is left on the surface of the plated workpiece. And in electroforming, the deposited material is much thicker and is separated from the substrate after plating to produce a separate part. There are three steps of electroforming. The first one is the preparation of a mandrel. After that, electroplating of the mandrel to the thickness needed, and the last step is separation of the electroplated material from the mandrel. This is the picture illustration of electroforming. This is the mandrel, and this is the electrode. And the last one is metal injection molding, MIM. Metal injection molding is a process somewhere between standard powder metal forming and injection molding. As used with many plastics, a mixture of fine metal particles and binders that usually include a thermoplastic, wax plasticizers, and dispersants is heated enough to provide a paste-like consistency and is injected under high pressure into mold cavity. The workpiece is then sintered in a vacuum that are similar with powder metallurgy. This process is carried out with low alloy steels, stainless steels, soft magnetic materials, copper, and other non-ferrous metals. This is the process of metal injection molding. Most of them is similar to the powder metallurgy process: weighing, mixing, after that blending, injection molding, debinding, sensoring, and packaging shaping. The difference is after blending, it goes to the injection molding process. If the powder metallurgy process, from the blending goes into the sintering process direct. This is the example video of metal injection molding simulation. This is the finished plastic part. And it fills to the mold. And it goes like that. Thank you for today.